Okay, about the support vector machine. This is a very famous algorithm. We can say that it has ruled the pattern recognition world in the decade from 1995 onwards. So it really, the roots of this go back earlier, but it created a huge stir, and there were literally thousands of people working in this direction. So they have been very influential, and they are the basis of quite a few of the talks that we will hear in the course of the seminar, which is why I wanted to give an introduction now. So I will spend most of this hour motivating the function that's being optimized in support vector machines, and will at the very end give an outlook on transductive SVMs, which is a specific kind of latent variable SVM. I won't say how to solve the problem, but I wanted to, at the end, give you an outlook on how this relates with latent variable methods, which are the main subject of the seminar. So first, this is a binary classification method. So we are given a set of training data. I don't mean to. So it's a good idea if you take a few notes. So I have a total of L pairs of points where xi are the features that describe the ith object in my training set, and yi are the labels associated with an object. The labels here are assumed to be either -1 or +1. So typical way to show this pictorially is well, something like you see in the bottom here, to have a sketch of feature space. So in this case here, we would have a two-dimensional feature space. And in this feature space, each object is represented by one point. And then I've here coded the labels by using different symbols and colors. And the aim of support vector machine is to learn the parameters of a hyperplane that will have small generalization error. So I want to automatically extract from the training set the rules, which are here encoded or expressed just in terms of a linear decision boundary. And if I have learned this rule well, then it will allow me to make valid predictions on future samples X that come from the same source. And I'm going to use this Eulerian form of representing a hyperplane. So let's say the origin of the coordinate system is here. Then I can represent a hyperplane. So in 2D it's a line, in 3D it's a plane, in 4 and higher D we call it a hyperplane. I can parameterize such a decision boundary by a normal vector W, and by its distance from the origin. So this distance is given by that much. Okay, so I can write from a hyperplane that x transpose w plus b equals 0. So in this particular case, if w is pointing away from the origin, then b would be a negative number. And actually there's a more compact way of representing this, which I will use later on. Well, namely, so in this 2D example here, I have x1, x2 times w1, w2 plus b. And I can represent this in so-called homogeneous coordinates. So I could write this is equivalent to x1, x2, and here a constant 1. And I multiply this with w1, w2, and b. I'm going to use these homogeneous coordinates in a plot later on. This is why I'm showing them now. And then I could summarize this in a new vector, which I can call w tilde, for example. Okay, so given is these sets of points in feature space, wanted are the parameters of the optimum decision boundary. And actually in this plot that I've shown here, all of these decision boundaries, a decision boundary always needs to say on which side do the red points sit. But if I'm saying that the red points sit on the side that I've indicated here, then actually all these decision boundaries are perfectly compatible with the training data. So you may like some better than others. So perhaps intuitively many of you would prefer the bold line. But at this point, the decision boundary or all of these are in agreement with the training data. However, I can also create decision boundaries which are worse, like let's say this decision boundary here. Then I would have a couple of errors. So this point here would sit on the wrong side, and that point would sit on the wrong side, and this one would sit on the wrong side, and that one would sit on the wrong side of the decision boundary. So in higher dimensions, when I cannot simply draw an appropriate decision boundary, I need to find it by means of computation. And to that end, I need some kind of loss function. So we want some measure for loss. That is the loss on the training data. So I want a function that tells me that this one here is bad and that these others here are good. Okay? Now, I want to argue that a natural measure is the so-called misclassification error. Which is defined simply as the count of the number of points that end up on the wrong side of the decision boundary. So I can write this as a sum over all points, the training set, the loss, so I have two L's now, well, never mind. Training set. And let me use a capital L here for Li would be the empirical loss of my sample xi, yi. So misclassification error is defined as, the first equation doesn't say anything, so the definition comes now, is defined as number of points that are on the wrong side of the decision boundary. So for example, all points I, which in fact belong to the positive class, and for which my decision boundary is predicting the negative class. So mathematically, I can express this as an indicator function. The indicator function is 1 if its argument is true, and 0 if its argument is false. So the argument has to be a Boolean statement, and the statement that I'm making here is to ask if the score that I'm getting from my method is smaller than 0. So I want to find parameters such that xi transpose times w plus b should be larger than 0 for all. So I want this quantity here to be larger than 0 for all positive training samples. And whenever this is not true, so whenever one of these quantities instead is smaller than 0, I augment my misclassification error by 1. Okay, so in words, the misclassification. Okay, well, actually, I need to also write it for the other class. So I need to have another term here. I'm also summing all training points which truly belong to the negative class. And I'm asking if they are on the wrong side of the decision boundary. So if xi transpose w plus b is larger than 0, even though it should really be smaller than 0. So in words, this misclassification error is simply the number on the wrong side of my decision boundary or decision plane. Because this expression here is a bit unwieldy, I can actually combine these two formula into one. As follows: I can sum over all points in the training set, regardless of what their class method is, and then multiply the score that I'm getting with the label, which we know to be either -1 or +1. And now I only have a single Boolean statement here. So if y equals +1, then this translates to the formula that we had seen up here. And if yi is -1, then multiplying this with -1 means that I can turn around the inequality here, and then it corresponds to this statement. So I have really only rewritten this into a more compact form. And this is now, I have previously introduced a letter for this. In the first line of this equation, I had said that generically I'm calling this capital Li for the contribution to the empirical loss of training set of training sample number I. So for the misclassification error, all of this would simply be Li. Okay, I can now plot this thing in terms of this aggregate quantity. So if I write yi times xi transpose w plus b, I'm now plotting this function here. Okay, if this quantity is larger than 0, then my indicator function is 0, and I incur no error. This is the red line. But if I'm on the wrong side of the decision boundary, then my indicator function jumps to 1, and I have this error here. Okay, so if I want to call this thing here, if I want to call this the score, then if I multiply it with a class label, this is the error or the contribution to the empirical error from a single training sample. So in a plane, I've parameterized it in terms of a normal vector, and here I'm just checking if any training sample, if I project it onto the normal vector and consider its offset from the origin, I'm asking if this is on the right side of the decision boundary or on the wrong side. Okay, and if I now plot for this set of points here, I'm now using this parametrization in terms of homogeneous coordinates that I was discussing above. So on the right-hand side is a plot with lots of information. This is, on the right-hand side, a plot that measures for each possible decision boundary its empirical error. So color-coded here is the empirical misclassification error. As a function of W tilde, which is simply my parameter vector W, so that was the normal vector, and the offset B. So in other words, each decision boundary here on the left-hand side corresponds to one single dot on the right-hand side. And let's look at this in a bit more detail. So the perfect decision boundaries like this one, they actually lie here in the center where the energy is lowest, or where the empirical error is lowest. If I have a surface that is pointing in the wrong direction, so if you now imagine turning this surface here by around this point by 90 degrees, then it's misclassifying everything rather than classifying everything correctly. And I've plotted here W in terms of its azimuth and elevation. So these worst possible decision planes, they are in the plot correspond to this region or to that region. You see I have a total of 20 points on the left-hand side. So the best possible classification error I can get is 0, and the worst I can possibly get is 20. Makes sense, I hope. Okay, and this plot, I can stare at these for a long time, because, for example, as I now change this decision surface, let's say I am moving it to the right, I will eventually come to a point when I start to misclassify the first samples from the blue class. And the moment when I misclassify a sample from the blue class, so I was starting here, somewhere at the optimum, and if I'm now, let's say, translating my decision boundary, this corresponds to a motion vector in this plot here. And the moment that I'm making my first misclassification, this is the moment when I'm making the first transition here from 0 error to an error of +1, and so on. And if you think about it a little, then actually the plot on the right hand side is a half transform of what we see on the left side. But if you don't know what a half transform is, never mind. It's a notion from image processing. Okay, so in this particular case here, I had 3 parameters. So I had my parameter vector w tilde, which consisted of w1, w2, and b. And in the plot on the right-hand side, I had furthermore constrained the norm of w tilde to be 1, which means all my decision boundaries sit on the surface of a sphere, and I have here unrolled the surface of the sphere. You know, this is like you can have maps of the world. On the right-hand side, you see a map of the misclassification error for all possible decision boundaries. And I can now do this in higher dimensions, so I can have a w tilde. You know, if you have, nowadays it's typical to compute very many features, so let's say I may easily have 7,000 features plus my offset, excuse me. Then I obtain a corresponding energy or empirical misclassification error surface, which is much, much higher dimensional than the one you show. And on this surface, we want to find the sweet spot. So the sweet spot, the area with the smallest possible misclassification error. So the sweet spot is this area here. Now, in a two-dimensional problem, you know, I can just see the sweet spot. Just as here in the primal domain, I can just see what is a good decision boundary. But in higher dimensions, we need some automated mechanism of finding it. And note now that this error surface here is piecewise constant. So either we misclassify a point or we do not misclassify it. So as I, you know, if I follow any trajectory here in this space of models, my error increases or decreases in steps of 1. So observations. One is that this error surface, or rather the misclassification error surface, is piecewise, and that, for example, rules out gradient descent strategies, which are, you know, something that you like in optimization. Normally you want to do a gradient descent. So let's say you know you want to find the lowest point on the surface, and you're initially sitting here. The gradient is 0, and there's nothing, you know, telling you if you should go right or left if you want to go towards lower energy or lower error, if I call this here the energy. Okay, so a piecewise constant error surface is hard to optimize. Now, so far we've been looking at so-called linearly separable problems. By linearly separable, I mean that at least one hyperplane or plane exists which achieves 0 misclassification error. But look at data sets like the one shown here on the bottom. However hard you try, you are not going to find a decision surface that makes no errors here. So whatever I try, let's say I'm trying this one here, alas, there are a number of points that are being misclassified. And on the right is again the corresponding misclassification error. You see that it no longer starts at 0, but it starts at 2. So apparently 2 is the smallest error you can possibly make here. If I've really matched the correct images, which I hope is the case. Now beyond that, look, something else has happened. Namely, the surface is still piecewise constant, but we now have local minima. So there's a local optimum here, and another local optimum there, and another one there. All of these are good local optima, but they are no longer connected. So another observation is that the misclassification error surface it may have local minima. If the data is not linearly separable. So up here I had written that the piecewise constantness makes it harder to optimize. And now that we have local minima, this means the problem is harder still. So, I started this section here by saying the misclassification error seems to be a natural loss measure, and I still think so. It's a natural error function, but it turns out to be one which is very hard to optimize, and that is something that we need to worry about in practice, because ideally, given a training set, given some model, we want to find the globally optimal set of parameters for this model. Now, both these observations that I made up here, both these statements are a consequence of the loss function being non-convex. So both observations the non-convex nature of the loss function. If you again look at the total error, this is the summation over all samples of the contributions to the loss from a single sample. And so the entire error surface that I've been plotting here is given by this summation. And if a single one of these loss functions is not convex, then the entire error surface is not going to be convex. And why do I go on about convexity so much? Because I'm making this as a general statement. Is the hallmark of, let me call this, friendly optimization problems. So I'm simplifying somewhat, but by and large you can think of it as follows. If your problem is convex, you're going to have polynomial complexity solutions, and if it's non-convex, then you're in the realm of NP hardness where everything is difficult. Okay?
Question.
Yes.
For example, if you augment your training set, can you use it as an heuristic for optimization in that one direction?
If you augment the training set.
Yeah, if you have more sample a little bit more, and you get like a direction for where the global optima of your surface is.
I don't see how that would work. So if I add more training samples,
so you would be lowering the error in certain direction in your surface.
So you see, each point. I was saying that this is a half transform. So actually, let's go back to the other plot. So each point in this space corresponds to one of the contour lines in the other space, and vice versa. Each plane in this space corresponds to a single point in this other space. Or actually, I should have drawn the point because this is one of the perfect lines. I should have drawn the point somewhere here. So we have this duality. And if you now add more training samples, if I add more training samples, it means that I get more contour lines in this space. I obtain a more complicated error surface, but it's still remaining piecewise constant, and it doesn't lift the problem of having local optima. What you do really want to do is to either smooth this surface and or make it convex. And essentially neural networks smooth this kind of surface, and support vector machines make it convex.
Okay, yeah, I was thinking more of your local, your non-connected areas are, if you augment the sampling, so some of them are going to disappear. I was thinking you get at least, instead of 4, then if you get more sampling, then you at the end get 1. And then you lose.
No, that's not true. It's not true. Okay, so yes.
The Heidelberg surface can have multiple parameters. So in the dimension example, it doesn't have to be a straight line.
So you are asking about non-linear decision boundaries?
Is this usual to do, or is it always
it turns out that it's enough to do the theory for the straight lines for 2 reasons. You can always take your training data and map it in a non-linear fashion to a higher dimensional space, and then again use hyperplanes in this higher dimensional space, which, if you project them back to the original space, are then non-linear entities. So that's how you can think about it, and that is true for any classification method. And this, and then in addition, there are certain numerical tricks of how you can avoid making this nonlinear embedding in a higher dimensional space explicitly, the so-called kernel trick. But conceptually, that's what you do. You take your original training data, which, for example, has just 2 features. Excuse me. Then you add more features. For example, I could add a 3rd feature, which is x1 times x2. Or I could add another feature, which is the square root of x1 times x2 squared, something like this. So you can invent any additional features that you like and append them to the original features. That is a nonlinear mapping to higher dimensional space, and in this higher dimensional space, you can then use a linear decision surface, and there is a reason for that. The so-called function counting theorem proves that if only you go to a space of sufficiently high dimension, and this mapping must be nonlinear, that's important, then you will always, with overwhelming probability, always find a decision surface that perfectly separates your data. On the other hand, this may result in overfitting, so sometimes there is an advantage in choosing a solution that's not a perfect fit, but that's an imperfect fit, but with somewhat simpler parameterization. Yeah, but this is why it's enough to look at linear models here only. Okay, so here's again the loss function that I drew before for misclassification error. And this is non-convex. By non-convex, I mean the following. Look, if I connect, let's say, this point and that point, I get a straight line which does not intersect with my curve. However, if I take this point and that point, then I necessarily here you see I intersect with my curve. And this is, well, how you can establish if something is convex or not. So in this kind of representation here, I'm looking for a curve on which I can take any 2 points, and when connecting these 2 points by a straight line, then I want this line to not intersect the body of which the curve is an upper envelope. So, let's say to obtain a convex error surface, I need a convex loss function. Now there is an infinite number of conceivable convex functions. For example, one that is quite plausible, I'm running out of colors, let's take this one here. One that is quite plausible is this one here. So this curve goes like e to the minus yi xi transpose w plus b. This is called an exponential loss, and this is in fact what's used by a method called boosting, which is a very good classifier also. And note that this is convex, yeah, so I can now take any 2 points on this curve, and I can connect these 2 points without intersecting the curve. Another one that's quite, something that you could do is you could take a parabola here. This is what you use implicitly if you use least squares regression. And there is a possibility to use something that incurs no error if the classification is correct, and an error that grows linearly with the distance of a misclassified sample from the decision boundary. This is now already very close to the support vector machine. This is called a central hinge. But we could also take the square of the central hinge function so this would be a squared central hinge all of these are possible convex choices. And as a reminder, what we really want to approximate is the misclassification error. So if I drew the parabola correctly, it would intersect here at the same point. Anyway, so the misclassification error looks like this. And now each of these loss functions has its advantages and disadvantages. For example, what's not so great about this least square regression is that you start to incur a penalty if a positive sample is very far on the right side of the decision boundary. So look, if the sample here is located on the decision boundary, but on the right side of the decision boundary, then you will have a penalty that is that high. And that is something that's usually not deemed desirable. Boosting, on the other hand, it increases, as an exponential function so if you severely misclassify a sample, then you pay a higher and higher penalty for this. Whereas the misclassification error simply asks, is a sample correctly classified or not, but it does not ask how far it is on the wrong side. Okay, so the support vector machine, the central hinge function is one particular compromise. So the central hinge function loss for correctly classified samples and incurs a linearly increasing a loss that increases linearly with distance from the decision boundary for wrongly classified samples. So linearly increasing loss for wrongly classified samples, where linearly means linear with from the decision plane. Now, being convex, the central hinge function gives us indeed a convex error surface. However, it also leaves us some choice. So, for example, the three solutions that you see here at the bottom, according to this central hinge function, they all have 0 center, because no samples are misclassified whatsoever. Now, we want something reproducible, so if you give me the same training set 10 times, I'm using the same method 10 times, I want to get out the same result 10 times, the same prediction model. And here, depending on how you do this optimization, it could happen if you optimize according to this loss function, because the loss function cannot discriminate between these solutions. It could be that one time you get the one solution and another time you get the other solution, and so on. Now, if you want to single out one of these solutions, there are different recipes that you could invent. One recipe is the following, to say, I want to put a margin around each observation, and I want my decision surface to not intersect with any of these margins. So here, for example, this decision surface here, it intersects with this margin and with that margin, so we can say that we rule this one out. This decision surface here intersects with that margin, so we can rule that decision surface out. And if you inflate these margins until just a single solution is left, then you can say that, in some ways that is a special solution. It's the one solution which has 0 error according to the central hinge loss, but which is furthest from all your training samples. Let's go back to this picture here and zoom in. There is this region here, the sweet spot, which is not a spot but a sweet area here. So all of these solutions have 0 classification error, and that for a support vector machine is called the version space. Again, each point in version space corresponds to one decision boundary that is perfectly compatible with all training data. And now, out of this infinity of possible solutions, you're looking for one which is special. And one recipe to choose one which is special is to say, okay, let's shrink this version space by giving, a margin. And if I shrink it further and further, eventually I will be left with just one point, the point that's sitting in a, if you define it in that way, in the geometric middle of version space. So the point which has the largest minimum distance to any of the surrounding contours, and you can say that is a truly special solution. And that's the one that we want to find. So the truly special solution is exactly the same as the one that survives when you make this margin around all points larger and larger until just a single solution is possible. And by the way, this is the solution that I here have shown with a bold line. Even though I just have scribbled this by hand, I've not computed this. So endowing all points with a margin, how can you accomplish this? And it's now that we come to the true support vector machine. So again here the famous plot of the loss function. This is the misclassification error, which is sometimes also called the 0-1 loss, because it's either 0 or 1. Then we have the central hinge function, which is 0 here, and then increases linearly. This was the central hinge. And now comes the thing with the margin. So we want to start, if we want to rule out solutions such as this one here, it means we want to start incurring a cost even if a solution comes close to a training sample, even though it's correctly classified. So we're not just happy with getting a correct prediction, we want the prediction to be correct by a margin. And that you can accomplish by saying that you want to use a function like this, where this is, let me call this the safety margin that you require. And this function, by the way, is the hinge loss. This is the famous loss of the support vector machine. So do you have any questions so far? So if here the score that I predict is correct and is in its magnitude larger than 1, then I incur no error. As soon as I invade the margin of my decision boundary, I start having to pay an error which increases linearly with distance. So in the spatial domain, I could say that this is my decision boundary. There is its margin, the margin for the positive samples and the margin for the negative samples. And if I now have here a member of the class plus, and let's say my vector is pointing in this direction, here I pay no error, here I pay no error, on the margin I pay no error, but as soon as I invade the margin here, I start paying an error for this distance here. And if I'm further away from the margin, you know, I have to pay more and more of this error. And vice versa for the other class. Here I pay nothing because I'm safely on the correct side. Here I pay nothing. On the margin itself I pay nothing. But as soon as I invade the margin, I have to pay a cost that depends on this distance here. And the further I am away, the higher my cost, and so on. So this is what the function says. We have, however, one problem left, at least for it's most clear for linearly separable problems, because so far we have made no statement about the magnitude of this normal vector W. So, for example, let's say this is the decision surface, and let's say it here just barely touches a sample of the positive class. If I forced my normal vector to have a magnitude of 1, then let's say the margin would lie here. So this is a distance of 1. And I could enforce this margin if I set the norm of W to be 1. However, if I let the magnitude of W be what it wants, then the classifier can make the margin very narrow by simply choosing the norm of W very large. So here the norm of W was 1, and there the norm of W is very large. So our minimization problem could look like this. We want to penalize, or we want to minimize the sum of these loss functions, and we optimize over parameters and b. And I could now say I want this such that the norm of W is 1, and by the way, this so if I want to write it in formula, the hinge loss, I could say so I now need to express this funny shape of the hinge, and I can express it by saying this is 1 minus yi w transpose xi plus b, the maximum of that, and 0. So again, if you remember the plot that we have, and this is what the hinge function looks like. Here the intersection is at 1. This part here is the straight line, and well, this part here is that line, and if I'm taking the maximum of the two, then I obtain my actual hinge function. Okay, hope that makes sense. So I could say that I want to minimize this thing such that the norm of W is 1. Unfortunately, this is not a convex set. So this constraint here is not convex, because it is the surface of a sphere. You know, I can draw a two-dimensional sphere, and if I connect this point on the sphere with that point on the sphere, then you know, I intersect the forbidden space in between. So this is not convex, and that again makes for a hard optimization problem. So instead, the support vector machine does something else. It simply encourages the norm of the normal vector to be short. This is a convex term, it's a quadratic term, and I now need to weigh them somehow with respect to each other. So I'm introducing some constant here that the user has to choose. And this thing here is a so-called regularization term. Favors solutions with small coefficients in the parameter vector. So you were asking before about, the nonlinear version and so on. When I project to a very high dimensional space, if I project my training set to a very high dimensional space, I have a great risk of overfitting. I now want to introduce a bias that says only use a feature if it really is strongly discriminative. And that I do by adding this regularization term, which does not make the coefficients associated with uninformative features, it does not make these coefficients exactly 0, but it makes them small. I'm rewriting this in another form, which is very common for vector machines. So it means we only consider the positive part. And this would be the absolute value, and putting a subscript plus here means we only consider the non-negative part of this, of those values here. And yet another way of writing the same is to say argmin WB plus C sum over I, and then hinge of yi w transpose xi plus b. There is yet another formulation which is equivalent, namely I can say I want to find the optimum parameters where I require that each point gets a score. So each point should have should be further than the margin from the decision boundary. So this is if I require strictly that each point should be outside the margin. However, I now want to relax this a little bit to avoid overfitting, or in non-linearly separable problems this would not have a solution at all. So I'm adding a so-called slack variable here. This is a slack variable, which is non-negative. This is for all I. But now I want to prevent the solver from, just giving me a solution which satisfies these constraints by simply choosing huge slack variables. So I need to penalize magnitudes of slack variables. I can write it like that. Perfectly equivalent to what you have above. And this thing here is now, if you look at it, it has a quadratic objective function. So we have a term that's here I now also need to optimize over the set of slack variables. It has a quadratic objective and it has a linear inequality constraints. And if you minimize a quadratic objective with linear inequality constraints, this is a standard so-called quadratic programming problem. A standard QP problem. And that is a very well studied class of optimization problems. And in particular, it's a class which gives you solutions in polynomial time. And of course, the problem is still convex. And actually, I've shown down here the get if you use the hinge loss rather than the 0,1 loss. So this arrow surface is for the same configuration of points that were shown before. So this is a standard QP problem, and it can be solved either by gradient descent, or it can be solved in the dual domain. There are many ways to optimize this. Do you have questions?
Those parameters C sent you so that it looks nice, classifies them?
Yes, this parameter C needs to be adjusted by the user. It's the fundamental trade-off between how faithful do I want to be to my data and how strongly do I want to regularize. And it is usually set by cross-validation, and the choice of the parameter really matters. So if you choose it badly, you will get the poor classifier.
And it can be automated via cross-validation?
Yeah, it can be automated, but you know it can be costly. In particular, if you now map to higher dimensional spaces, this is associated with more parameters, and hence you quickly get a large number of parameters that you should optimize in cross-validation. So that makes it computationally expensive. So that is one limitation. Another limitation is that fundamentally it's really only a binary classification method. So if you want to discriminate between more than two classes, there are either some very expensive formulations that try to do it all in one, but it's more common to then train one class against all others. So if you want to discriminate k classes, you need k classifiers that are all one trained in a one against all fashion. So what I've not talked about is this dual representation. This can be achieved rather mechanically. So you can use Lagrange multipliers to represent these constraints and add them to the objective in order to obtain a Lagrangian. Doing so, of course, requires Lagrange multipliers, and you can then finally obtain the so-called dual optimization problem, which is formulated in terms of these Lagrange multipliers, which I will just write down without showing the transition between the two. You find this in any textbook, or you can look at the video lecture recording of my pattern recognition lectures from the semester, which you find somewhere on YouTube. and I mentioned in passing the kernel trick, note that the feature of a single point here never appears alone. It only ever appears in an inner product with the feature of another observation. And this fact can be leveraged to replace this. So rather than simply use the inner product here between xi and xj, I can instead replace this and use some function. And there's a big choice of what sum could be. The only condition is that the resulting matrix, if I write this kernel matrix down between each observation, each training observation and any other, the resulting kernel or gram matrix has to be positive semi-definite. That's the only requirement. That still leaves you a large choice of what these functions can look like. All right, and that brings me to the outlook. I promised to mention a bridge to latent variable models. So the so-called transductive SVMs for semi-supervised learning. Consider the following problem. Assume that you have many unlabeled points. And a few labeled points. So let's say, in the extreme case, I will have one labeled point here and another labeled point there. That is the setup in semi-supervised learning, and that is quite representative of the real world, where you have never enough patience or time to annotate all of your training data. So let's say you work in image analysis. A single image has millions of pixels, and then you may have thousands or millions of images. So if you want to train something that gives you a per pixel prediction, you will never have time to annotate all these pixels and associate them with ground truth information. So for semi-supervised learning, more formally, I could say that I have training data part yi with I running from 1 to L. These are the labeled observations, labeled training observations. And then I have further observations xi with no label, unfortunately, where I runs from L plus 1 up to N. These are the unlabeled observations. And N, the total number of objects, is L plus U. So N is total number of objects, L is the number of labeled objects, U is the number of unlabeled objects. Now, if we forget about the unlabeled data, then, I would obtain a classifier that looks something like this. Because, or did I get the angle wrong? I think I got the angle wrong. Let me try again. If I have two labeled points, then my optimum classifier will be orthogonal to their connecting line and just in the middle. So this would be the fully supervised SVM solution. What I tried to suggest by the choice of the gray points here, or by the distribution of these gray points, what I meant to imply is that a much better classifier would lie somewhere here. So implicit, let me try again, somewhere like here. Implicit in this is the so-called clustering assumption, namely that points which are well clustered in feature space will tend to have the same label. So let's say that this is the desired result. Can you agree that this would be desirable? At least that is the tenet of semi-supervised learning. Yeah? The green solution here is preferable over the blue one. So how do we do it in terms of math? I want to again find the optimum parameters and slack variables. I have again the regularization term. I now have two constants. CL is the constant associated with the label examples. So this sum goes from 1 to L. Plus, I now have an extra term CU for unlabeled, which is associated with the slack variables of all the unlabeled examples. So here the summation goes only from L plus 1 and then all the way to N. That. I again want that my predictions are correct by a comfortable margin up to some slack which I am permitting. No, minus was correct. And the slack has to be non-negative. Now this holds for all samples 1 up to n, so for the labeled and the unlabeled samples. However, note that, so if I say that this holds only also for the unlabeled samples, note that we still need for them some label in this equation. And this is now what I optimize over in addition. So I optimize over all of the above and also over the labels YL plus 1 up to YN. So a total of U labels, which turns it into a combinatorial optimization problem. So I have a continuous optimization here for these first parameters, and because the labels must either be +1 or -1, I have a combinatorial optimization problem over these unknown, over these latent class labels. So this is what I also sketched here. This is the missing information. These are latent. And because they can either be +1 or -1, that is not a convex set that I'm optimizing over. Because of that, what I have here is a hard, non-convex optimization problem. Which was first studied by Wapnick in the 70s and then by Thorsten Joachims in the late 90s, I think. I've written down, so it was published in JMLR 2008, but I think it's much older than that. And I also quote here a recent review on different approaches to optimizing this hard problem. There's a minor technical difference here. This review takes not the slack variables, but you can raise these to some power. And in this paper here, they use p equals 2, so they use not the hinge, but the squared hinge in their comparison. So there you are. By introducing these additional class labels for the points that I had marked as gray here, you step from the friendly realm of convex optimization to a very hard non-convex optimization problem. And much of this seminar will be concerned with, on the one hand, models like this, models involving latent variables, and on the other hand, the advanced optimization strategies that are required to optimize these well in spite of this missing information.